Also go vote today. I don't remember what the Wisdom Wednesdays is. What is that one? It's tomorrow. What was it, Charles? About hunger, that's right. So, yeah, go out and get some lunch. All right, let's pick up. I have a lot of things I want to talk about today, and we are rapidly running out of class periods. We'll have one more to go after this one, so let's see how far we get. But just to quickly recap where we left off last time, we're talking about what causes relief. The earth doesn't look like a billiard ball, but there are mountains and different features on the earth. And so we started talking about things that create this relief. Of course, volcanoes, active volcanoes, volcanic features, things left over from volcanoes. Went on to talk about other circular features, won't go into detail, impact, events, also lack of this. This is magma material that comes up from below and bulges out and creates then areas at the surface that reflect that. This can be caused by salt. I mentioned the Carolina Bays in the southeastern United States, interesting circular features that have defied explanation. And it's interesting to drive around the southeast and look for these things. Or go to Google Maps. They're very plain, very easily visible. And one of the compelling ideas, not proven yet, of course, and I don't know if it could ever be proven, but is this ice splatter theory where you had something from outer space impacting, and they estimate the location in the vicinity of Saginaw Bay up in Michigan and creating in this pattern. Looking again at the buildup of material, you find various kinds of rocks resulting from this buildup. Of course, igneous material, lava flows of various sorts around the globe where active volcanism is occurring and where it has occurred in the past. And these are very plain. I took this picture out close to Cedar Breaks in Utah. Basalt is very common. Lava that moves toward the surface doesn't spew out of a volcanic cone, but will flow out along the surface or near the surface, cools rapidly, and fractures in this characteristic manner of columns, joints. Granite is also an igneous rock that's formed from the cooling of the magma, the molten material, usually deep beneath the surface, cooling fairly slowly, and creates typical crystalline pattern that we see in granite. Some of the hardest rocks in the world are metamorphic rocks. These are rocks that were formed at some time in the past, have been reheated, remelted, exposed to new pressure within the crust, and oftentimes you can see evidence of the previous structure. So some of this banding would reflect sedimentation or sedimentary rocks, but then the remelting, the reheating creates very hard rocks. And things like gneiss, schist, mica, marble, slate, all of those are metamorphic rocks, and again, very hard, a lot of them very ancient. So the three categories of rocks are sedimentary rocks, igneous rocks, and metamorphic rocks. And you see those across the globe at the surface and beneath the surface. Most of the crustal material, that's the hard stuff that makes up the crust above the mantle, is made up of igneous rocks. But the sedimentary rocks are the ones that actually cover the surface in greatest percentage. So 75% of the surface is actually covered with sedimentary rocks. Okay, so we began talking last time about things that act within the crust, things that are going on, pressures and tensions that build up. These things cause earthquakes. And I talked about faulting. Earthquake is caused by dislocation occurring within rock structures under pressure, and eventually those structures break and you have that dislocation. And the point I wanted to make here is that this is happening down beneath the surface. So you may get disturbances at the surface, but it's not necessarily where the primary rupture occurs. Talked about the various elements of this, seismic waves, how you can measure the different kinds of waves, tell where the earthquake occurred, and you can also get some evidence about the interior structure of the earth based on the propagation of these waves through the material within the earth. So all of this is useful to us. Various kinds of faults. One of the most common types of fault is a slip fault or a strike fault, where you have lateral motion of this material. This is one of the most famous in the world, the San Andreas Fault in California. The western part of California is moving off to the northwest, whereas North America is rotating down to the southeast. So you get this rupture. Yeah, Jim? Oh, is that right? Yeah. Well, we could spend a lot of time. It's a very interesting fault. There are areas, such as in the Bay, which have generally not moved very much. And of course, there are a lot of subsidiary faults. There are some areas of the faults which have been in motion, and so they have periodic earthquakes, and so those are not the dangerous ones. I have to look that up. That sounds interesting. Makes you wonder if that's a precursor to some major event that might be coming. So call your relatives in San Francisco and warn them. Get out of Dodge. Here's a picture. These are typical of faulting areas, and they often show up as visible on the surface. So that's the San Andreas Fault in areas of, not sure where that is out in California, but anyway, earthquakes, frequent. Another thing that can happen is folding, where the increasing pressure, buildup of pressure, doesn't cause breakage, but it causes the wrinkling and the deformation of the rock layers. So you get these typical folding kind of environments. Here's the area up near Harrisburg in Pennsylvania, and you can see normally you get these long ridges, ridge and valley areas. In this part of the world, they trend from the southwest to the northeast. And I talked about this last time, the various parts of the fold, the synclines, bottom of the fold, the anticline is the upfold. And sometimes you have synclinal ridges. You have areas, this is the area around Birmingham, Oak Mountain, Double Oak Mountain, as you cross these ridges as you go from here into Birmingham, and they're very evident, very plain. A lot of times rivers, this is the Delaware River, will cut right across the ridges because it's superposed. That means it was there first. And here you see a water gap through one of these ridges as the river has made its way and cut right down through it. Here's another view of it. So anyway, we talked about all of that last time. Just one more point about folding I thought I would mention. There's something that happens on occasion in certain areas of the world, and I want to illustrate it here in this area of the northern Andes. In South America, the Andes split into 2 or 3 branches. You have the central Andes, or the central range here in Colombia, and then the eastern range. This central range peters out right in this area. And so you have the flat valley of the Magdalena River flowing up through this area. Here's the Cauca River, the Magdalena. And then all of a sudden, this little knot of mountains up here along the coast that can get up to about 15,000, 16,000 feet. Those are the Santa Marta Mountains, way up there. Well, what's happened here in this part of the world is the Andes, high mountains of the Andes, have actually, in this area, they dip down and go deep underground, thousands and thousands of feet underground, the same rock structures, and then they pop up again to the north. So this is folding on a very, very large scale. They call this a warp. So here's the area. The actual mountains of the Andes are way down deep below the surface, and then they come up and expose themselves again right along the coast of the Caribbean. And that happens in a few areas around the world. So this is called a warp. Okay, what I want to get to today is what causes all this stuff. folding, volcanoes, earthquakes. There's stuff going on. There are tensions, there's forces. There are forces operating within the surface or within the planet, within the crust, that's creating. It's not static. It's very dynamic. Well, plate tectonics. So there's a picture of broken plates. So that's what we're going to talk about today, plate tectonics, which is probably the most important theory to have emerged in the earth sciences, certainly in the last 100 years, and maybe forever, because it goes a long way toward explaining many puzzling observations that people have made about the surface over the recent decades and years. So here's some of the things people puzzled about. What you're looking at here is pillow lava. Much of the bottom of the ocean looks like this. This is igneous stuff. This is what happens to lava when Kilauea lava flows into the ocean. That's what it looks like. And so this happens underwater. As water cools the lava, it looks like this. So a lot of the bottom of the sea looks like that. Now you might expect, if you didn't know anything about the earth, that the bottom of the ocean would be sedimentary. You'd have all of these layers of accumulated debris from marine organisms dying and runoff from the continents into the oceans. As the bottom of the ocean would be filling up, but that's not the case. This is igneous material. You may have a very thin layer of sediment of the lime stuff or the limestone, but it would be very, very quickly, as you dug down, you get into this kind of stuff. Another thing is, if you go down to Antarctica, you see this. These are coal seams, all this dark stuff. And coal, we know coal is formed in a certain kind of environment that where you have forest in tropical or subtropical environments. And so the trees fall and decay or partially decay, overlaid by mud. So we know what those environments are. They do not exist in Antarctica. There are no trees, there are no forests in Antarctica. So how is it possible to find coal down at the bottom of the planet? So that's something that puzzled people for a long time. Here's a map that shows major earthquakes between 1900 and 1999. And you can see they are highly concentrated in certain areas. And they are absent, generally absent, in other areas, eastern Brazil. Now, there are some in the eastern United States, but these are the major earthquakes. Australia has very, very few earthquakes. So why the localization of these earthquakes in this area? We refer to this area around the Pacific as the Ring of Fire. So anyway, John turned it down a little bit. But anyway, I was going to play the song by this famous geologist here.
Love is a burning thing.
Okay, we'll move on. Notice also the localization of volcanoes. These are the active volcanoes, and there's a place you can go on the web and check which volcanoes are erupting currently. And I think I mentioned the other day, and Gordon was with me, we were traveling through the Straits of Messina between Italy and Sicily, and we went right by two volcanoes that are erupting. One is Etna on the island of Sicily, and then Stromboli, which is a big mountain sticking out in the middle of the ocean. And so here you can see the erupting volcanoes in the month of September. And notice again the localization, and also notice the correspondence to some extent with the Ring of Fire. They generally occur in similar areas to where those earthquakes were occurring. So people have puzzled about that for a long time. You know, why the high level of localization? Why not uniform or randomly, let's say, distributed around the globe? Another thing you might do is look at the oceans. Here's the Pacific Ocean, big body of water. If you were traveling to the Earth from the planet Mars and never been here before, what would you think about where the deepest part of the ocean would be? What would you think? I mean, probably out in the middle, right? This might look like a bowl of soup or something. And yet, if you look at a profile of the oceans, it looks like this. You have areas of underwater mountains, and then you have some deep areas, but they are canyons, underwater canyons, and you can see them on here. They generally occur not too far from the major continents. So here they are. These are the deep areas. These are the canyons. So that's unexpected. It's not what you would imagine. It's not, you know, what makes common sense. And notice the correspondence as well. So here's the Ring of Fire again, and the major deeps in various areas. There's one off Puerto Rico. Here's the Atlantic Ocean, and there's a mid-Atlantic ridge. There's an underwater mountain range right down the middle of the Atlantic Ocean. So again, sort of goes against common sense or what you would expect. One of the most intriguing things has been analyzing the shape of the continents. For a long, long time, people have speculated about South America and Africa. These look like puzzle pieces that you could just shove them across the ocean and they would fit together. And not only these areas, but also you can find similar over here, Madagascar off the coast of Africa. It looks like it came off of this, broke off of this coast. And there are other ones too that I didn't highlight. For example, Antarctica fits in here in South America. And so people have speculated about that. So the idea that the continents were joined together at one time has been around for quite a while. If you examine the offshore platform that exists along all continents, the continental shelf, the fit together between the continents is even better than if you're looking just at sea level, the outline of the continents. So again, here's some evidence that at one time these areas were joined together, but something has caused them to split apart, to go their separate ways. If you look at ancient fossils, here's a fossil that's found in this area of Africa and in South America, and nowhere else. Mesosaurus. The idea was first proposed by this fellow, Antonio Snyder Pellegrini, back in the 19th century. And he had the idea that the continents just somehow they plowed across the ocean and moved away from each other. Didn't know anything about how it might have happened or mechanism. A lot of people laughed at him. Another fellow came along, Alfred Wegener, German scientist, and he was more of an explorer than he was a geologist. Geologists also discredited him because he wasn't officially trained in geology, but he basically had the right idea that in fact the continents are drifting apart. They're moving away from each other. And so we understand that today. And but it took some further research to understand how and why this is happening. And it's led, he proposed the idea of continental drift, and that term has stuck with us, so we still talk about the drifting continents, or continental drift as a process that's ongoing and reflected in the surface features that we see today. Well, we need to talk a little bit about magnetism. And as you know, magnets have polarity, north and south polarity, and they have force fields associated with them. And these force fields can be found, can be determined. And the Earth itself, of course, is a magnet. And that's why you can make use of a compass. A magnetized needle will orient itself in the direction of the magnetic polarity of the Earth. Will point north or point south depending on the magnetic field or the orientation of the compass. Now the magnetic north is offset slightly. It's not exactly at the North Pole, and remember there was a little video presentation about that, I guess, on the first day of class. And one thing that's interesting is that it's moving around. It doesn't stay in exactly the same place. One thing that happens is lava, igneous material, when it cools, acquires the magnetic polarity of any magnetic field within which it finds itself. And all lava then cools within the magnetic field of the Earth, so it acquires that polarity, and we can analyze it. And then today we talk about paleomagnetism, ancient magnetism. We have the capability, we have the instruments today that we can analyze the magnetic polarity of rocks of various sorts and say something about where the pole was at the time that these rocks cooled. These two guys, Bernard Brun and Montanori Matayama, all the way back at the beginning of the 20th century, they proposed the idea of pole reversal. And eventually they got around to proving it. What they did was found some igneous rocks, areas along volcanoes that had been erupting for long, long periods of time, volcanic deposits, and analyzed the magnetic polarity of these rocks from the surface, the newer rocks, all the way down to the older rocks. And they found that as they got down to some of the lower levels, the polarity was just the opposite of what it was today. So today's rocks may point north, oriented as the compass is oriented, but as you get down to older rocks, they point south. And so this has been discovered, or this fact has been discovered, that the magnetic pole of the Earth has reversed itself frequently over the history of the Earth. And the last time it reversed was 780, I need another zero there, 781,000 years ago. And here's some of their descriptions of diagrams. And so it just flips completely. It goes from south to north, north to south, and it does so very rapidly in geologic terms, maybe within 1,000 years or so. So if you take something like iron, and again, think about the Earth, and expose it to a magnetic field as that stuff cools, and it will take on that magnetic polarity. And that's what happens to the rocks. Now here's the magnetic reversal diagram showing the blue would be the normal, that's the way it is right now, and then the red would be the reversed field. And so these two guys gave their name to these first period reversals, and we have identified additional reversals going back in time. And so here's a short diagram. Over here to the right, this is present, and moving off to the left, this is in millions of years, 10, 20, 30, 40, 50 million years, continue down to the next line, and then on down. And so this is as if it were all strung out from right to left here. And notice you have a long period here. In fact, it's called the Cretaceous Normal Superchrome, where for, what is that, something like 30 or 40 million years, it was all pointing the same way. And so this is irregular. Sometimes it lasts for a long period of time, sometimes not. And so they've discovered additional long periods extending on back in time. So this was information we didn't have before. This magnetic polarity associated with the rocks, and the fact that the Earth's field reverses itself, and reverses itself fairly dramatically, almost suddenly if you're looking at geologic time. Well, a couple of other guys came along. And this is they did the research in the late 50s and early 60s. The critical article came out in Nature in 1963, Matthews and Vine. And what they did was they took a magnetometer, an instrument that can measure magnetic polarity, this orientation, and they pulled it behind a boat across the Atlantic Ocean. And then they just recorded what was happening in their magnetometer. And what they discovered was this kind of thing. In fact, these are charts from their article. This up and down movement of the readings that they were getting off the bottom of the sea. So here it is illustrated. They were getting these kinds of readings. Now, the Earth's magnetic polarity today we know is oriented again toward the north. And I won't use positive or negative because positive is attracted to negative and that can get confusing. And so there was something that was periodically pulling against the polarity of the Earth, registering in this magnetometer. So there was something in the rock's polarity that was tugging in the opposite direction. So basically what they determined is that the rocks at the bottom of the sea were displayed in bands with reversed polarity. North and then south, and then north and then south as they moved across the ocean. Yeah. They tried a bunch of different directions, but essentially what we're looking at, and I'll get to it in a minute, is a pattern that's perpendicular to the axis of rotation. So going from east to west, west to east, more or less. So this should clarify it. Okay, so they were working eventually in the vicinity of the mid-Atlantic ridge. So you take an area like this, and here is the pattern that they came up with. So basically, these lines, these zones, were oriented parallel to the mid-Atlantic ridge and perpendicular to the pole, I guess. Is that right? Well, anyway. So this gave them the idea, and this was the key discovery of what was going on, what's happening here. Basically, magma material is coming to the surface in the vicinity of the mid-Atlantic ridge, this underwater mountain range. This is an area of volcanoes. Iceland is essentially one big volcano. And you have a variety of other ones, islands periodically. So you go all the way down to the South Atlantic, and there's an island called Tristan da Cunha. It's just a big volcano. So every once in a while, these volcanoes erupt at the surface, but most of it's under the water. But it's volcanic material. These rocks are being cooled right now, and so they are acquiring the magnetic polarity associated with the Earth's current magnetic field, pointing north. But as you move away from the currently formed rocks, you get to other rocks that point south. Well, those are rocks that were formed at the mid-Atlantic ridge, but during a previous time period when the magnetic field was reversed, when your compass would have pointed south rather than north. And then you move further, and then they're back north again. And so what you're getting in these stripes along the bottom of the ocean is a chronology of the reversal of the Earth's magnetic field, back and forth, back and forth. And you can match up the time periods when that reversal, when that field remained for a long period of time in one orientation, or generally you get a wide band of rocks. And then when it's a short period, then you have a narrow band. And so you get correspondence. Another thing that happens is the width of the bands matches on either side of the mid-Atlantic ridge. If you have a wide zone west of the ridge, then you have a corresponding wide zone east of the ridge, again indicating the length of the period when this was happening at the mid-Atlantic ridge. And so that's the process by which South America and Africa are being pushed away from each other. And today we know that the speed is about 2 inches a year. That's how fast that opening up is taking place. So having explained all that to you, here you can see it moving. You also have areas where areas are coming together, plates are coming together. When that happens, generally the seafloor will dip beneath the continents. Continents are generally made up of lighter rocks. Granite, for example, is lighter than the heavier igneous material that's along the seafloor, and so the seafloor will dip beneath the continents. Continent will ride up over it. You have friction being created in these areas and escaping to the surface. And so having explained all of that, now you can look at a picture of it.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is...
Okay, so cut it off there. All right, we've used a lot of analogies for plate tectonics. I'll just show you a couple of them. One is a cracked egg, a hard-boiled egg, where you can see all the cracking of the shell here would represent the various plates. Another analogy that's often used is a conveyor belt. So the plates are in motion at the surface, and then you have counterflows down beneath of the magma material or the molten part of the magma moving in the opposite direction. Another applicable analogy is this one. I tried to find a good picture. That where the tubes here represent the continents. They're being pushed and bumped around. So a lot of the continental crust material, the stuff on the dry land, doesn't really get circulated back underneath very much. It's usually the seafloor that goes down because it's heavier. And so it's like peelings or scum or something floating on top of a liquid body where the conts periodically will bang into each other, and then they'll move away and get smashed up and distorted. And so a lot of the rocks on the continents, some of them go back, half or even maybe 2/3 as old as the planet itself, never really getting recycled back in. So anyway, some analogies there. But essentially, well, that's what I just said, I guess. So going back to the puzzles that we talked about just a few minutes ago, why is the bottom of the sea mostly igneous? Well, it's because the bottom of the ocean is not very old in geology terms. It just hadn't been around long. It's part of this creation process that's going on constantly. Why do you get coal deposits in Antarctica? Well, Antarctica has not always been at the South Pole. During other times, it's been much closer to the equator, and it's moved to that area. What about the Ring of Fire? Well, we'll talk more about this in a little bit, but the volcanic activity, the earthquakes, even the trenches are associated with these areas where things are bumping into each other, coming together, moving beside each other, where That's where the action is. That's where you're getting these pressures, tensions from rocks being locked together, splitting apart, breaking apart. So these are the areas of tectonic activity. Areas such as eastern Brazil over here, there's not much happening there in terms of tectonic events. There's some mountains, but they're old mountains. They were formed a long time ago. They're being worn down, weathered by the action of the climate. Similar northern part of North America. These are areas that are very stable. We'll come back and talk about all of that in just a minute. And of course, you look at the shape of the continents, well, they look like they're parts of a puzzle because, in fact, one time they were joined together. They were part of the same supercontinents that existed here in these areas and these parts of the world. And again, the deep trenches, these are areas where one plate is descending beneath another one, generally where some of the seafloor is dipping beneath a continent or beneath another ocean plate. These are known as areas of subduction. And so subduction areas are where you're going to find the deepest areas of the ocean, whereas out in the middle of the ocean, as we saw in the middle of the Atlantic, you have underwater mountains where it's spreading and a variety of other things are going on. So this theory, this idea of plate tectonics, which is as accepted as any theory, certainly in the earth sciences these days, will explain many of these things that we've been talking about. Of course, it raises many other questions as well, and we'll come back and look at some of those in a minute. So as we try to reconstruct what the Earth or what the land areas look like, if you go back about 250 million years ago, most of the continental landmass was all together, was all bunched up together. And we call this Pangea. Someone asked me, well, who named it that back then? Well, there wasn't anybody back then to name it. People have not been around that long. But we call it that, Pangea. And then at some point, as we go forward in time, the northern area split away from the southern area, and we've named these two Laurasia and Gondwana, or sometimes Gondwana land, to reflect the northern half of Pangea and the southern. And then you begin to get the breakup of Gondwana and to some extent Laurasia to the north. There's still plenty of evidence of these ancient continents around. So I'll come back and refer to this later on. But if you look at the purple area, these are areas that are called shield. These are the areas where you see at the surface the fragments of the ancient Laurasian supercontinent. Now, all this other stuff, again, we'll talk about that, but shield areas refer to fragments or portions of these ancient continents that existed at one time. Here's what Gondwana looks like, the southern continent, and you still see a lot of shield areas within this. Notice the position. Look where India is. India eventually migrates across the Indian Ocean to slam into Asia. Another thing that's interesting is you can find common fossil evidence within these areas. Again, fossils distributed, and I had to ask Jacob Dane to translate that for us. It's in Dutch, but it was the only map I found of it. So eventually, here we go, 65 million years ago, you can see again Madagascar is pulled away from Africa. India again has started moving away. Antarctica has started moving south. I'll show you one more video, then we'll break. The middle of the map here is going to correspond to West Africa. And you can see as it will end up, but all of these land areas are what eventually forms the continents that we know today. And this is our best idea or estimate. Obviously, nobody knows exactly for sure. Now here you're beginning to see areas that will eventually turn into the Appalachian Mountains, where these continents have banged in and bumped and withdrawn. So now you begin to see Gondwana forming, areas of Laurasia to the north. Watch India begin to move across the ocean. Inland seas in Africa, even South America. This is a Tethys Sea up in here. And you have the pleasure of listening to Beethoven's Moonlight Sonata. Okay, let's break and we'll continue with this here in a few minutes. Come back quick because I got a lot to say. Need a gavel. Okay, so let's continue and talk a little bit more about this business. Have a lot more in the way of maps to show you. The purple area here, these are shield areas, sometimes referred to as cratons. So either term is fine. And so all of these areas here are essentially slabs from the ancient continents that have been drifting away from each other. Some up in the north, and then these down here in the south. These would be the Gondwana shield areas. And they're very stable. They may include mountains, but there were mountains that were formed a long time ago and have been stable over a long period of time. I'll mention a couple of things about eastern Africa here in a little bit. So these are the shield areas. And again, Gondwana in the south, Laurasia in the north. And together they at one time go back and formed Pangaea. Let's talk about how, a little more specific about the formation of some of these things. Here is a physiographic map of various kinds of features. The purple area is what's referred to as the alpine system. So all of this. And the little dots or the lines, you can ignore that for the time being, but that refers to different characteristics of the rocks or of the landscape, valleys or mountains or whatever. And so these areas are alpine features. And what that means is they are relatively recent in geologic history, formed not too long ago. And they refer to the areas where the plates are active, where things are bumping into each other, where you're getting subduction, where you're getting movement. So you can see the San Andreas Fault would be within that region. These are areas that are currently active. These are the areas of the Laurasian Shield. That's the yellow areas up here. So these are very stable. These are just fragments of these ancient continents that have been drifting around for millions and millions of years. What's referred to as the Caledonia or the Appalachian areas, these are areas that were active at one time, would have been part of the alpine system, but are no longer active. It's where mountains were formed. The Appalachians, of course, went through a whole series of different stages where the mountains were formed and destroyed and rebuilt. Right now, what we see in the Appalachians are evidence of ancient mountains, older mountains, but there's nothing going on there at the present time. It's just being worn down by the continued action of weathering and erosion. So every year, they get a little smaller, a little more worn down to base level. Nothing happening, at least not at the present. Doesn't mean it won't happen in the future, but at least not right now. And then finally, this area, the green, would be sedimentary basins. These are areas where the prevailing rock within the crust is currently sedimentation, sedimentary basins where you have accumulations of the things we've been talking about, shale, sandstone, at the bottom of ancient seas, deposited over long periods of time. much of it overlaying more ancient rocks that lie beneath. So if you go to South America, you have the same features, the Alpine system, the Andes, youthful mountains currently active. Again, the sedimentary basins, but then also the Gondwana shield areas here in the south. These fragments of that ancient continent that existed down here many millions of years ago. What's happened in South America, of course, is you have South America moving away from Africa, originating from this mid-Atlantic ridge. And then we have the Nazca Plate that's bumping into South America over here along the western side of the continent. Nazca Plate, the seabed, is dipping beneath South America, so all the volcanoes, the earthquakes, all of that stuff that's happening in the area of the Andes is because of that contact between these two plates. The movement is constant, the rocks get locked together, eventually something breaks, you have the release of the tension of the energy, and then we have an earthquake and the devastation that those events cause. So that's what's going on here in the eastern part of the western part of South America. Here's Africa, and a couple of new features here in Africa. One is some areas of volcanism. These are just flows of volcanic magma, more or less unexplained by, the actual motion of the plates. Probably a hot spot of some sort. We'll talk more about that later. But the main feature in Africa is this area that's referred to as the rift area of East Africa. The most significant features in Africa are not alpine mountains. Notice that there are no mountains of the alpine system except the Atlas Mountains up here in the extreme north. But what you do find are volcanoes and events associated with essentially the spreading apart of Africa in this area of the Rift Valley of East Africa. I'll come back and talk about that in a minute. More areas of the Alpines. Of course, the Alpine system is named after the Alps because the Alps are indicative of what mountains are like within that area. Essentially, Europe is moving toward the south and creating disturbance in the process, and eventually what is the Mediterranean Sea will be a large mountain range. All of this stuff will be pushed up in the air, and all the sediments at the bottom of the ocean here will be up in the high elevations of the mountains. Now, we won't be around to see it, but take my word, it'll happen. And then as you move on to Asia, notice that most of East Asia is part of the Alpine. All of this is active. Middle East, all the way through East Asia, Japan, the islands. So earthquakes, volcanoes, they happen all over here, everywhere. With a few old continental fragments, a few shield areas, such as in Australia, India, and some of the Caledonian Mountains up in Siberia. So basically, that's what the world looks like. These are the physical remnants of these ancient continents, and also the areas of contact where things are happening. So I mentioned a couple of them. You have Europe moving to the south. The highest mountains in the world were caused by India migrating across the Indian Ocean and ramming its way into Asia. It's like a bulldozer. It's just pushing up all those mountains of the Himalayas, the Hindu Kush, the Karakoram. Those are all created by this action of India, and it's ongoing. Those mountains are getting higher as we speak. So here's what's happening in Africa. You've got the rift area in East Africa, and it shows up as a series of lakes, valleys. Here's Lake Malawi. This is how you're actually looking south here from north to south. But this is part of the rifting process. Just like the middle of the Atlantic Ocean, its areas are moving away from each other. And so Africa is spreading apart. It's a little bit further along up here in the Red Sea, just beginning down here in some areas further to the south. But if we were to live long enough, we would see another ocean open up here between this area of East Africa and West Africa, because these continental portions are moving away from each other. Here in the middle of Africa, it actually splits in two, the rift. So you've got one, the western rift, that's progressed a little bit more, and you can see it in all the lakes here in this region. And then there's another one that comes down east of Lake Victoria. Victoria sits right in the middle of this. And so the higher mountains, Mount Kenya, Mount Kilimanjaro, are associated with this eastern rift over here. Again, this is magma material coming to the surface, created by this opening up process. Further north, you can see it. The rift extends on up through the Red Sea. It's progressed into the valley of the Jordan River, the Bekaa Valley, all the way on up, goes all the way up into Syria and Turkey, further to the north. And so it's a major rift area. Now, there are other rift valleys around the world, but this is certainly the biggest and the most dramatic. There's Kilimanjaro. Look at the snow. You won't see that much longer. I thought I'd do a little bit of a run-through of something that happened a few years ago now, I guess about 7 or 8 years ago. Remember the earthquake in Haiti and how devastating that was? Yeah, 2010. Killed, it's actually over 230,000, more than that. And then if you add in the disease that came after and everything else, the death toll was very, very, very large. And of course, it hit the country one of the countries in the world that could least afford it, one of the poorest nations, and tremendous hardship. Well, here's a sort of a geology or a landform map of Haiti. And the thing to be aware of, all these lines on here, these are faults. Most of them active faults. And the one to keep your eye on is this one right here. It's called the Enriquillo Plantain Garden Fault, EPG, right through there. Now, Port-au-Prince, the capital city, sits right there in that little crook. So notice the fault goes right through there. Now, if you look at the plates, again, looking at the plate tectonics in this area, there's a small Caribbean plate here in this region with the various kinds of motions. And on the northern border of this Caribbean plate, the blue areas are areas of subduction. That's where things are going down. The yellow areas are areas where they're sliding beside each other, these slip or parallel faults. And so, in particular, I want to look at this little area right here that's called a microplate. This region right in here. And notice the movement here that these things they don't happen nice and smoothly. They're jagged, and you get things locked together and breaking apart. And so you have the northern area along this microplate moving to the west, and then along here, moving to the east. All right, these are major earthquakes in the decades prior to 1910, the localization. And notice that they're located right along the edge of these plates, of this microplate. It's called the Gonavi microplate. But notice something interesting. Not much had been happening over here in the eastern part of this plate. Not many earthquakes. Now, the longer you go between earthquakes, that means the more pressure, the more tension. And so when the rupture happens, it means there's more energy to release, more force. So when the earthquake came right in here, there was a big release of energy, a big release. That there was a lot of movement, a lot of shaking. Shaking lasted a long time. And so that was the reason. It was because all of this had been locked together, had not been moving along as it had over here in Jamaica and southern Cuba. And so when it happened, it was a major, major event right in there. Okay, let's talk about North America. Let's see what time it is. Okay. Remember, the Laurasian Shield would be the purple areas. There have been major mountain building events in the western part of the continent and over here in the eastern area. The center region has been largely, throughout much of geologic history, has been an area of inland seas, lowland areas, again, where you would get accumulations of sediment. Now, I've got a little arrow here pointing to where Alabama is, so you get a feel for it. This is 360 million years ago. And again, this is a reconstruction based on the best evidence that we have available. Notice that here, what is the area around the Appalachians, there had been some previous mountain building events. I'll come back and talk about those in a minute, but not much happened out here in the west, at least not during this period. This was all underwater. But as you move forward in time, again, due to the continental motion, the plate motions, you eventually get the Rocky Mountains being formed out here. And basically what happened here was there were major plates coming off of the Pacific from left to right, from west to east, that ended up dipping beneath much of these fragmented areas here that at one point were just a shallow sea, and in the process pushed up what eventually became the Rocky Mountains. Now, this is during the Cretaceous, so getting toward the end of the dinosaur period with all of this. Question comes up, well, how old are the mountains? That's not something that's easy to tell. Because if you ask me how old are the rocks, well, here, if you've been to Colorado Springs, this is one of the prettier areas of the Rockies. You have in the foreground here the Garden of the Gods, and that's Pikes Peak in the background. Pikes Peak, the rocks at the top of Pikes Peak go back almost 2 billion years. That's almost half the age of the Earth itself, way, way back. But they have not always been where they are. Of course, they were formed much earlier, and at one time, as I just showed you, were down beneath the sea, beneath the water. So you go back here 360 million years ago, and there was hardly anything out there. We use the term orogeny to mean mountain building event. And so there have been repeated orogenies long before this, but the most recent is called the Laramide. Garden of the Gods, as the mountains of the Rockies were being built and Pikes Peak was being formed, all of these layers of sedimentary deposits here within this region, so here you see Colorado right there, all of those layers then get pushed up and deformed and distorted by the action of the mountain building process. So the Gardens of the Gods are sandstone slabs that are almost vertical. If you've been there, you've seen them. They just stick straight up in the air. These slabs, but they're sedimentary layers that were deposited flat at the bottom of the sea at one time. And so all of that mountain building process has tilted and distorted those things and made them stick almost straight up in the air. During this process where Pikes Peak and the other mountains behind them were being formed. So this happened during the Cretaceous, and you had continued uplift. Now it happened, and again, this is kind of brief and might seem complicated, but you had a series of plates here along the eastern Pacific, here's North America, that were moving into the continent. And the most important were called the Kula and the Farallon. So you're getting subductions of these plates beneath North America. And so here's kind of a sequence. Notice this is 30 million years ago. Here comes the plate. The brown is the continental mass of North America. So here's the Farallon plate coming along. Pacific plate right behind it. And notice we're progressing. These things are beginning to move under the continent. The Farallon plate's gone. Now we've got something called the Cocos plate, Juan de Fuca, which is still creating the Cascades Mountains up in the northwest. Continued pushing beneath. And so eventually we're here. And in the process, not only is this stuff going under the continent, but we're getting this lateral motion as well, where these plates are moving somewhat to the north and to the south. So main point I want to show you here is that this is not a simple process. There's a lot of complex motion going on here as one plate dips beneath the continent of North America. What gets pushed up in the air are all the sediments of the ancient oceans that existed out here. So all of this stuff, here's Monument Valley, pretty area, another pretty area, this sandstone in this canyon. All of that gets lifted up because of the action and the pressure of these plates going beneath the surface, pushing all that stuff up in the air. And of course, all the layers of the Grand Canyon, the Colorado Plateau, all that going up in the air. Here's a profile of it, and I'll spend a little bit of time on it. This is what they refer to as a staircase. And what I did was I took half of the image and then I added the other half on up here. So this is really a continuation of this over here to the left, all right? So the Farallon plate has come beneath the surface and remaining fairly flat has forced this area up in the air. Now, there have been some volcanic action here and there in the past, but all of these are very old rocks that are being pushed up by this portion of the crust that's been dipping beneath the surface here. And the thing that's interesting is this stuff is it's been maintained more or less flat or parallel to the force, or perpendicular to the force, pushing up in the air. So you get the various layers here within the Grand Canyon. But all of this dips down lower as you move north, and you pick it up over here. Now here, down here, where my pointer is, these are the things that are exposed in the Grand Canyon. But they're sitting beneath a lot of other stuff that's up above it, which over here has been worn away. And so here's Zion Canyon. Zion Canyon doesn't cut down into the layers that the Grand Canyon did. They are further down beneath. And so I'll just pick one of these layers. This is an area, this is called the Navajo sandstone. And it's either pink or white. If you travel out west, you see it a lot. And this is an area known as the Escalante staircase. So if you travel out here, Barbara and I on the road out to Boulder, Utah, and just stopping and looking, taking pictures. So you see stuff, this is all Navajo sandstone. It's all that stuff that's been pushed up in the air by the action of this Farallon plate dipping down beneath us here. Some places it looks like this. Some places it looks like this. And here you can see the cross bedding, see the streaking. That's usually indicative that this was formed not at the bottom of the sea, but in a desert like the Sahara where you have sand dunes, going in different directions. So you get this kind of striation. All of that. In Zion, this is, if you look up in the park, you see all of this then is that Navajo sandstone. In this case, there's some iron in it, and so it gets more of a pinkish or a reddish color. So it's all part of the result of this Farallon plate dipping beneath the surface here. Well, here you see it. That's all of this area. And of course, you have all the other layers as well, looking at all of this. And so here's the diagram of it. The thing that's interesting about this particular event is that this plate has remained fairly flat for a long distance. So it comes in off the Pacific, goes down, creates the Sierra Nevada, forms the ridges and the valleys in Nevada, in the state of Nevada, and then it gets all the way over here into Arizona, and so this is the area that we're looking at. Some areas you've got, again, the friction and the melting and the volcanoes, so that's not uncommon out there. But it's created this uplift along the Colorado Plateau. They can do seismic analysis, again, looking at earthquakes and various kinds of evidence coming through the material beneath the surface. And they have actually reconstructed what the Farallon plate currently looks like. So here's a sequence, again, 80, 60, 40, 20 million years ago. And so it's gradually sort of wrinkled up down here beneath the surface, but it's still there. And some argue that it extends all the way into the eastern United States. I don't know if it comes that far, but there have been a few earthquakes in, let's say, New Madrid in Missouri. Some have said maybe that's related to the presence of the Farallon plate down in those areas. So interesting history. Okay, talk a little bit about the Appalachians. Here you can see areas. The Appalachians reflect continued banging together of areas that today are South America and Africa. They've bumped into each other, moved away, bumped into each other. So you've had various events that have created different sets of mountains at different times. The last one, of course, was the Appalachian. You've had these repeated collisions. If you go back almost a million years, you have what they refer to as the Rodina continent. Now, it's all kind of fragmentary. Here you can see fragments of current continents. But we're looking at this area right in there. That's the region of the Appalachians. Again, pointing out Alabama, notice that all of Alabama at this point, this was before Pangea, all of this was essentially underwater. This was all, and this goes back, you know, the coal deposits in Alabama and all of that came later. Well, all of that formed in sedimentary layers during this period. So here comes Africa pushing off, colliding, and eventually we have formation of Pangea, all of this in one big landmass. This area, as time goes by, South America begins to pull away, move south, again pointing out Alabama. Notice we have the mountains caused by this collision here. And as time goes by, then you begin to get the various formations. Even as late as 75 million years ago, a lot of Alabama was still beneath the ocean, but fragments of the old mountain building still here in the area of the Piedmont. So when you look at a diagram like this, all of these areas in the red, these are the results of ancient mountain building events, and all these names refer to those events. And the main ones affecting the Appalachians in this area, let's see. Well, I'll come back and mention that in a minute. If you look at the current geology of this area, and I know a lot of you had Mike Mason's course last year on geology of Alabama, so repeating some of this here. But you have an area that divides the coastal plain in this part of the world from the Piedmont and the Appalachian Mountains. And this is often referred to as the fall line because as rivers flow across this boundary, the areas that make up the Appalachian and the Piedmont are much harder. They are igneous material, they're metamorphic rocks, and they're very resistant to erosion, whereas soft rocks in the yellow areas here wash away more readily. So it's called the fall line because rivers will go downhill, they'll fall. The sedimentary layers here in these yellow areas are softer and they get worn away more readily, more easily. So here are some of the mountain building periods in the Appalachian that referred to. Grenville, Taconic, Caledonian, some of these more up to the north. So part of Scotland was associated with this mountain building here in North America. And of course the most recent one, the Allegheny Appalachian, that was about, this period soon after Pangea, or that formed Pangea. It's a complicated process. You'll have mountains built and then destroyed, continents pull away and then come back. So you'll have barrier islands, maybe with volcanoes. Here comes Africa again, jamming into this area, just show you. You'll have fragmentary evidence. So here are the remnants of maybe one of those coastal islands with volcanoes, the volcanic arc. You'll have areas of magma. The little orange areas within here would be areas of magma that solidified underground in the magma chamber. Eventually these things become exposed at the surface and referred to as plutons. That's what they look like. You travel throughout the Appalachians, you have these rounded, bald spots. These are all igneous formations or metamorphic that were formed in the core, in the heart of the crust, and eventually exposed at the surface. There's a famous one, Stone Mountain. There's some in South America, Brazil. So profile of the Appalachian looks something like this. You had basically sedimentary deposits to the west. You have this constant back and forth bombardment by the continents of Africa and sometimes South America. And in the process, they would push up mountains. There are fragments of more ancient mountain building experiences here in the east. And then they would withdraw, and then they'd come back and bang again. In the area immediate to the west of this mountain building region, you have the wrinkling up of these sedimentary deposits caused by the force or the pressure that propelled all of this stuff into the sedimentary layers laid down by the oceans. So this would be the Ridge and Valley area. So areas like Birmingham, Alabama, or all up through most of western Pennsylvania, that's the region of the sedimentary layers that were formed by the action occurring basically along the region of the Blue Ridge here in the Appalachian Mountains, this constant banging back and forth. And in the process, you have coal deposits within this region, but most of this is limestone, shale, some sandstone, but not as much as out west. So that's generally the profile of this area. It's caused by this constant back and forth banging together of these continents here within this part of the world. To draw it a little bit closer to home, as we're moving closer forward in time, 50 million years ago, notice that the coastal area is beginning to dry out as the sea shore recedes. And looking at this area now, here's the fall line coming through here, and if you look carefully, the fall line comes right through this area. In fact, if you go out to Chihuahua State Park, the little waterfalls out there, that's the flow off of the Piedmont down onto the coastal plain, and you can trace it. Now there's great difference in the age of the rocks here. So all of these rocks of the coastal plain are much younger. And so this area right in here, this is the oldest of these sedimentary. This is called the Tuscaloosa Formation. And it's kind of a sandy sort of substance, but it's hundreds of millions of years more youthful than the things just to the north of it. So look at that in a little more detail. These areas, this area of being crunched back and forth again by these various mountain formation periods, the rocks get older and older as you move from upper left to lower right, partly because what happens is deeper and deeper stuff gets pushed to the surface by these events. If you look from down here, the sedimentary layers get progressively older as you move to the north. But again, all of this is much, much younger than that stuff up there. So, to show you a quick profile, this is from if you want to know anything about geology of Alabama, this is a good book by Jim Lacefield. So you see all of these sedimentary layers, they all dip down toward the coast. And they're older and older as they get back here. And here is the more ancient rock that begins to show up north of the fall line, up in there. All right, now getting real close to home here. All right, I've drawn Interstate 85 on the map. Here's Auburn, and here's Opelika. This is a geology map. Now, I'm not going to go into all the details of the different kinds of rock types here at the surface, but just be aware. Yeah, let me see. Okay, here's the fall line coming along here. Most of this stuff up here to the north is all fragments and remnants of these ancient mountain building processes over the millions and millions of years, going back almost a billion years, where continents have crunched together. And so most of this is either igneous or metamorphic. Very hard rocks, very resistant. Most of this, when it breaks down, when it weathers, turns into some kind of red clay, or that's basically the kind of soil you would get out of that. The areas down here to the south, these are more recent sedimentary rocks, and most of this would be more of a sandy consistency. And what you will, let me see what I've got next. Okay. So here, if you look at all the, and I've shown you just a couple of, notice, main thing I want you to notice here, this is all metamorphic. Schist, marble, quartzite, gneiss, this is all hard metamorphic stuff, all of these colors up here. This is all, it's Tuscaloosa, but it's all sedimentary, and a lot of it unconsolidated. But what I want to point out, if you think about where you live in Auburn, more or less, notice that it's mostly the underlying geology is this metamorphic stuff, but periodically we still get some of this sandy stuff. In other words, the sediments of the Tuscaloosa group overlaid this, but they've been washed away to some extent. And so if you go out Highway 14, some pretty good farming out there because you've got better quality soil out in those areas. I know our house has some sand deposits. It's not clay and red clay like you find in some of the other. Anyway, so scattered about through this area, you still have some remnants of some of this other stuff. Actually, the oldest rocks in the state of Alabama and some of the oldest in the southeast are down here in this corner, down in this area. If you go out down toward the Seal area, out toward the east, you get very, very ancient rocks. So in a nutshell, that's kind of the geology of this area. Let me go ahead and stop here because you may have questions. I've gone through a lot of things, and it's all been very brief and in a nutshell, but hopefully it gives you some general idea of the transformations and the processes that have gone into shaping not only the continents of the world, but more specifically some of the things that have been happening here in North America. Now really, I've got about 2 more sessions worth of things to talk about, but we're going to squeeze some of it into next time around. I still want to talk about some other features related to plate tectonics. For example, there are things that are referred to as hot spots, where periodically you have magma, molten material comes to the surface. That's what formed the Hawaiian Islands. It explains what's going on in Yellowstone. And so we'll talk a little bit about that, talk about islands, talk a little bit about the oceans, because again, most of the surface of the earth is water, it's not land, and yet we've been focused on land. So we're not going to do a lot of oceanography, but I want to just give you kind of a taste or flavor. And then a little bit about the interaction between humans and this physical environment. There's so much we could say about climate change and modifications of the landscape and negative impacts of human occupation. Not all of it negative, but a lot of it. And so we'll come back and pick up with some of that, and then time will be out and we'll be done. So let me see if you have questions. And if, yeah, Frenchie. Yeah. Mm-hmm. There are estimates of where all of this is going, and what I'll try to do then before the next time is bring in, there's several predictions of, given the current movement of these things, and what can we forecast, or what's going to happen into the future. Nobody knows exactly, but pretty good idea, pretty good guess, given the current motions of the plate. So it's a good point. Thanks. And one thing too, before we finish up with plate tectonics, and I mentioned this a while ago, even though this theory or this model answers a lot of the questions, a lot of the puzzles, and allows us to put things together and understand what's going on to a great extent, there's still some very fundamental questions that we don't have full answers to. For example, the most important, why does it happen? Why are these things moving around? What's the force? What keeps it going? and other things as well. There are details about location of important mineral deposits and all that's all related to this. So we'll come back and talk about some of those things as well. Yeah, go ahead, Bill.
So maybe what you were just saying, my question won't get answered, but all these plates are floating on molten magma, I guess magma is molten.
Yeah.
They're currents, like, they're both floating on the ocean water.
Well, they're really attached. So the analogy of the floats in the pool is not exactly right. They're hooked on to stuff beneath, but at some point they are in motion relative to what's happening way down deep. There are various levels of plasticity within, from the hard crust all the way down into the earth. Now you're looking at material that's under extreme pressure and tension, and so even the hard solid rocks under certain conditions will move and will flow, in kind of a viscous manner. Trying to think of a good analogy, like syrup or something that will, and so if things are moving in one direction at the surface, you have to assume that there's something going in the opposite direction down below. So that notion of a conveyor belt, holds up, at least according to most theorists. But yeah. Eventually, it will all be ground up into, whatever mountains and stuff, the Himalayas, and if that motion continues. Now, what happens is, for some unknown reason, the motion will go, and then it'll go back off, and go the opposite direction. And so, it's not necessarily continuous until it disappears. We just don't know. Or you take Africa and North America, well, they've collided, but they don't just all end up in mountains. They'll come to a point and then they'll back off. And those are the kinds of things we really don't fully understand. And so, maybe researchers 5 million years from now, after observing this, will be able to figure it out. But I think, and this goes for much of science, especially astronomy, I think we do an amazing job, not we, but the scientists who come up with all this, do an amazing job of developing theories and models and ideas based on very scanty evidence, based on very limited evidence. So, we talk about galaxies and stars, and, you think about what the evidence that's behind all of that, it's quite limited. Okay, well, we're probably out of time. Y'all, thank you.